61A, Lecture 16, Q&A.
Well, while we're waiting for a question, let me ask you, John, what do you ever use the non-local construct?
Um, it's pretty unusual to use it. The truth
Yeah,
is that mutable values and non-local assignment are quite interchangeable.
yeah,
And Python was originally designed without it, which is kind of interesting.
yeah.
And then there was kind of a push from the community that gives feedback to Python that they should support this because it is a kind of natural thing to do in specific circumstances where um, you're trying, for example, not to use mutable values, but you still want to have like certain functions have access to some value that's in a
Mhm.
parent frame. So it also kind of comes up in the context of this course as we talk about higher order functions enough. People wonder how come I can't kind of change things in the enclosing environment that I can read from. Well, it turns out you can.
Yeah,
But the consequence is very similar to the consequence that you get with mutable values, which is that now functions might change how they behave.
yeah.
And this is kind of the simplest possible way to do it, but you could also do it with a list or something like that.
Yeah. I'm not crazy about the construct. There's something about it makes me uncomfortable. Anyway, I didn't realize that it wasn't part of the original Python, but it does have that feeling of something that was added in later.
Yeah, the particular way in which Python allows for non-local assignment, which is that you have this non-local statement, is weird, and
Yeah.
that is clearly a symptom of them adding it late.
It was an afterthought. You can see the construct.
Yeah.
Okay.
Okay, so the question was about when a list refers to itself, like what's going on there. And there was a particular example from lecture last time that I think it looked something like this,
Yeah, that looks right.
something like that. Well, let's talk about this example. So a very curious thing happens here where when you try to display this, you get something that's not just full of one, twos, and threes and lists, but also this elided portion. This is an ellipsis, basically to say this is just the whole thing all over again. So if you look at what's actually in here, the len of t is 2, t0 is 1, and t1 is just t again. And there's lots of ways to get a list to contain itself, but they all do involve some kind of mutation, like assignment, or sorry, like a slice assignment, which we have here, or using append or extend or something like that. And what we've done here in particular is that we've said replace elements from 1 to 3, so that would be element 1 and element 2, with the contents of this list. And the contents of this list is actually just one element. That element happens to be t, and so you get this structure. And this I find not the most easy thing to read. So I prefer looking at this as an environment diagram so you can kind of see what's going on. And if we do the same thing there, we'll see that one of the elements of t is in fact t.
So while John's doing this, notice there's two things going on there. There's how the list is being stored, and then how it's represented when you try to print it. And those are distinct things.
That's right. So this is the storage is this. T is a name for a list with two elements whose element at index 1 is that same list. And then how on earth would you print this out? Well, Python does it this way.
Yeah. So the representation of the list is finite, but the printing of it is infinite because you have to keep referring to yourself. You keep chasing your tail, essentially.
A follow-up question was, could you refer to the 0th element of the first element of t?
Good. Let's try that.
You could. So once you got t1, that's just another name for t. And so its element at index 0 is just the number 1. And in fact, its element at index 1 is just t again, and that's t, and that's t, and that's t, and that's the 1 at the beginning of t. So I could have an arbitrarily long referring expression, But really all we're doing is just deciding how many times we want to re-refer to the same thing. The question is about how you compare different node labels in a tree that don't have kind of a direct relationship. Like comparing the parent to a child, pretty straightforward, because whenever you have a tree, you can refer to the parent label as just label and the child label as the label of a branch. But what happens when you want to compare things that are kind of farther apart? And that does involve recursion, usually, and some mechanism for getting the information in one part of the tree available as you're processing another part of a tree. So I guess there's two kinds of questions. There's questions that involve just like some fact about all the labels, like what's the second largest label in the whole tree. And in those, you kind of want to process the whole tree, but as you go, you need to keep track of what's going on. So I think you'd have to keep track of both the biggest and the second biggest thing you've seen so far. And whenever you see something that's bigger than one of those, then you need to kind of update that. So that's one kind of problem. And another kind of problem might be for two nodes at the same depth, but not necessarily direct siblings, which one's the biggest or something like that. Or like, yeah, what's the largest difference between two nodes that are at the same depth? And this it similarly involves just processing the whole tree, but at the same time, keeping track of an additional piece of information, which is what depth you're at.
But let me offer another thought here is processing data in a tree is just a slightly more complicated than processing data in a list. So in a list, you have neighboring elements, right? Their index is different by one. In a tree, you have the parent-child relationship. But if I want to know, for example, as John was just saying, what's the smallest element in a list, I've got to traverse the whole list. If I want to know what the smallest element in a tree is, well, I have to traverse the whole tree. And there's a couple different ways of doing that. You can go all the way down and then start making your way back. And then the only other example I could think of too was that same notion of maybe you want to, because there's another sort of dimension, if you will, to a tree. It's just not the ordering, there's sort of the depth ordering. So that's the only other thing I can think about, in which case, as you're traversing a tree, you have to keep track of that information and then sort of analyze things at the back end.
Okay, let's take a look. So the question was about this quiz 4 from the exam prep section, question 1. A quant firm has enlisted your help in maximizing their trade profits. You know ahead of time how much profit you will make by executing each trade. These values are stored in a tree. However, if you decide to trade a stock represented by some node S, you are not allowed to execute trades that have an edge directly connected to S. For example, if you choose the parent, you can't choose the child. I think that's what's going on. Return the maximum profit you can make based on these constraints. And then there's a skeleton, which involves saying, oh, the profit of the tree involves calling a helper on a tree, and something that we're going to track. That something might be whether we are allowed to do anything on this level or not, or it might be something else. I guess we'll see. So I guess, unfortunately, it appears that this question is using a representation of trees that we have not taught you.
Yeah.
And that we do not plan to teach you in this semester. So I would say that the template here is problematic and we should ignore it. Instead, try to solve the problem using the tree representation that you do know. Because we don't have any like none trees and we don't have any lefts and rights and things like that. But we could still solve this problem with the tree representation that you do have. And how would we do that? So profit of a tree. Let's get ourselves an example. Return the max profit. And here's an example tree. Oh, it's a big one, isn't it? 2 at the top. We've got a 3. My goodness. It's going to take a while, isn't it? Maybe it was a mistake to do an example. Maybe we'll do a small example, and then we can make it larger if we really feel like it. Okay, so in this particular tree, if I took the 2, then I wouldn't be allowed to take the 3 and the 4. But if I take the 3 and the 4, that's allowed because they're not directly connected. I guess we need to make it just slightly more interesting. And we'll put a 5 down here. So if we take the 4, we can't take the 5. But we could take the 3 and the 5, or the 2 and the 5, or the 3 and the 4. And the best would be to take the 3 and the 5, which would give us 8. How might we do this? Well, I agree we need to kind of keep track of some information as we go, basically to decide, am I allowed to use the values in this part of the tree or not? And there's a constraint which I think says, once you've used a label, you can't use any of the labels of its children. So if I were to come up with a helper, I think it would take in tree and say whether or not we had used the parent. And at the beginning, there kind of is no parent, so we don't need to do that. Used parent. Okay, so if we use the parent, then we're not really allowed to use any of the current labels. The best we could do is return the sum of the results of using the branches.
Hey, John, in the chat, Steve is saying that you can't use as children or parent.
Well, that's right. I think that if you impose the constraint that, like, if I don't use the parent, I'm allowed to use the children, and I do that everywhere,
Yeah.
then I've kind of covered the constraint in all ways. Like, basically, as long as I make sure that whenever I use a parent, I don't use a child, then I've also made sure that, like, whenever I use a child, I don't use the parent, because it's kind of symmetrical that way. Well, that got long, didn't it? But if I don't use the parent, then I kind of have to decide, like, am I going to use this current label or not? So I think I have, I could use it, which would mean that I have the label for T as part of my result. So I've used the current label. All right, let's do it this way. We'll add to the total everything that we find in the branches. Or I could start with a total of 0, meaning I don't use the current label. But that means I'm allowed to use the children. Then I think what I want to do is, well, maybe the total is the wrong word. Well, okay. Total plus equals the sum of everything I use below, where I'm deciding whether I use the label or not this time. Something like that. The hardest part of programming during these things is that Zoom has put, like, all kinds of stuff on the screen that I'm trying to avoid. Oh. Clearly this did not work. Making up a problem and trying to solve it together seems to have caused an issue.
I think what the chat, maybe somebody in the chat said you have to compare the two totals. And I think that's right.
Yeah. Okay. So this is what I was supposed to do.
Yeah.
There's kind of a version where we. Okay. So this is like a total 1, and there's a total 0.
Yeah.
It's a terrible way to write it. But we'll do it this way anyway, and then we'll clean it up later.
Do you need 2 different used labels now? Oh, no, you don't.
Well, I kind of.
Although I think you should.
Okay, so that works. Okay, so let's write this like a normal person would write it, which is basically like keep making it longer. So this is the use label total, and then the skip label total. Which involves, I'll write this out explicitly, not using the current label, but in this case, you don't get to use the children, and in this case, you do.
Sorry, John, what's label 0? Yeah.
Well, we're getting close.
Now you have to fix your max now. Yeah.
We're getting there. Okay, so it passes for our one example, and I guess you have to trust us that it passes for the rest of them. This expression here and this expression are the same. So there is another way you could write this, which is to kind of assign this to a name and use it twice, and that would probably be a reasonable thing to do. But in both cases, I guess we are illustrating exactly the general principle we were talking about before, which is that sometimes as you traverse a tree, you have to keep track of information about the rest of the tree that you can't see right now. So at the very beginning, you can see the whole tree. But later on, as you're making recursive calls, you can only see the current node and what's below it. If you need information about what's above it, like whether you included the parent in the total, then you need to keep track of that information by passing it in as an argument. And this recursive call is telling the function that's going to process this branch some information about what's going on above that branch.
That's a good comment. It's the chat says we always see people who know the solution solve the problem. Seeing the way someone approaches a problem for the first time is really helpful. I think that's true, by the way. It's always easy to solve the problem when you know the answer. It's good to see this sort of iterative approach and the mistakes that we make.
Okay, well, let's see. Yeah, great question. So why is it the case that when you're performing local assignment and also trying to read a non-local variable, you get the error in the wrong place? So let's illustrate this with an example and see why it seems like it's the wrong place. You get an error here where everything we know about Python so far says that there should be no error here. You want to print x plus 1, so you figure out what print is. It's in the global frame, no problem. You figure out what x is. You don't find it here, so you look here and you find an x, and so this should print 4. All programming languages have some quirks. This is a particularly nasty one that exists in Python. It exists, I think, because you know, there are two central concerns in programming language. Well, there's many concerns in programming languages, but two of them are it should be easy for the user to express the program that they want, and that program should run reasonably fast. There's this particular optimization I think Python does, which is that it has a constraint that says all the names within a function that are the same, so like all the x's within this body of G, have to refer to the same frame. That's just like a restriction that exists in the language. That means you can't have two x's in the same body where one refers to the global frame and one refers to the local frame or something like that. And they do this so that, like, basically when you're figuring out what your program means and you're going to execute it, it's easy to figure out like where in memory something lives, I think. I think it's sort of an optimization. But why isn't important. I think as a programmer, you just need to know that this is a constraint. So there's no way to write a program that kind of accesses this x and then changes an x in here. And this line would, in fact, change an x in here as opposed to anywhere else. This is local assignment. So why is it that you get the error here instead of here? Well, in some sense, you could say, like, Python's broken. And that's a perfectly reasonable reaction. There is an error. So whether it shows up here or here, I don't know if it's that big of a deal. Like, there's a problem with this code, and Python is telling you there's a problem with this code, and so you got to go fix it. I would have, if I were designing the language, I would prefer for the error to like come up somewhere else or to say something other than this, because this is particularly misleading. The error really is that you're trying to use an x from the F1 frame and then assign to an x in an F2 frame, and that isn't allowed. X needs to refer to one particular variable in a particular frame whenever it's used multiple times in the definition of the same function.
So one way to think about it is the problem is not so much line 4. It's really the combination of line 3 and 4. It's that you're using the variable in different ways. So if I had taken out line 3, line 4 would have been fine. So that's one way to convince yourself that, you know, it's the combination of the two lines. So you may as well do it in the first one. But it also means that Python knows what's happening downstream, right? It's not blind to the code it is about to evaluate. Yeah.
Yeah, this is the particularly spooky part, I think, for students who see this is like, you mean Python knows the future of what the rest of the code looks like? And in fact, it does. So there's multiple stages to interpreting a program. And one of them is just to read the code and make sure that all the parentheses line up and all the brackets line up. And actually that happens for your entire Python file before anything gets executed, is that it kind of does a syntax check. Now, that syntax check in Python tends to be a little bit more involved because it's trying to set up the program to run quickly. So it doesn't just make sure the parentheses are matched. It also figures out that for every name, which frame is it going to refer to? And so it has kind of looked ahead at your code to figure out, is this a local X or is this a non-local X? Like, where in the environment is this X going to be? And it saw this line and determined it was going to be local. And then when it tried to execute this, it didn't find that X defined yet. And so that's why you got this particular error. But that's just like a detail of how the interpreter works. Not so much about the language, but like about how the language mechanics actually run, which I guess now you know. But the mistake of having X try to refer to two places at once is something that like everyone should know, because that's a constraint about the language.
And by the way, I agree that the error message here is awful. Right? They should be able to give us a better error message than that. Yeah.
The next question was about summer 2020, midterm 2, question 7. All right, I guess I'll have to read the question. Here we go. The village operation takes a function apple that maps an integer to a tree where every label is an integer. A tree T whose labels are all integers, and applies apple to every label in T. To recombine this tree of trees into a single tree, simply copy all of its branches to each of the leaves of the new tree. Wow, I definitely need an example for that.
Mm-hmm.
Oh, I don't know about these exams I didn't write. Okay, so if you have a tree, if you have a function that builds a tree of x, x plus 1, and x plus 2, and a tree that looks like that.
Yeah. Oh, I see. So I think what's happening is,
I see, all these branches showed up here and they showed up here. Okay, that sounds reasonable. Fascinating.
So
Let's take a
am
look.
I understanding this right, John, that it creates two trees, one with the result of x plus 1 to every label and one to the result of x plus 2 to every label, and then creates the parent?
No, it finds the root label, 10.
Yeah.
passes it into this function to create 10, 11, 12.
Yeah.
And then for every branch of the old tree,
I
it
see it. It
does the
duplicates.
same thing, except it does it multiple times. It does it here, and well, I guess I can't highlight this.
I see. Right. So,
It does it
okay.
here, and it does it there.
Gotcha. Okay.
Okay.
Ooh,
So
this exam.
we get a helper function called graft, which says graft the given branches onto each leaf of the given tree. And then we're going to call graft on some tree and some branches. And your question was, how come these aren't part of graft? Or how come they're indented the way that they are? This structure says, define a new function called graft, which in principle has access to the apple function and the t, which we might need.
That's what's confusing.
And then after you're done defining this function, build some new things, a tree and some branches, and then call graft on those two things.
But let me just start with one obvious thing, because I didn't notice this until you scrolled up, John, is that graph function is embedded in a larger function. So the
Right.
three lines that you're seeing there, base T, BS, and return, are the body of the parent function. It's just that the comments are so long, you can't see the header.
All right, let's see if we can make some progress, because why not? So we need to call apple on the label of the tree. We need to kind of recursively do this, I think. We either do it now or we do it later. It's not clear to me how this is set up.
John, can you make that a little bit bigger?
Oh, sure.
Thanks. Ah, better.
So I guess we need to know what we're going to graft on. And that will be the result of calling village on a branch of tree using apple. Apple's the first argument for every b in branches of t. Okay, now we do the grafting. And what does that grafting look like? Well, if t is a leaf, then to graft these things on, well, what a strange structure we have here.
So are we making a tree? Do we have to return a tree with T in the node and BS as the children? Is that right?
I guess what we could do is we could graft these branches on onto all the branches of the tree.
I was thinking that was going to be our base case. I wasn't expecting a recursive call there.
Yeah, I'm just trying to fit the template.
Yeah.
Okay, so now we've got a leaf. Oh, I see. So they're trying to set us up to do this here, I think.
Yeah, that makes more sense.
Seems like this template has multiple possible solutions, but we'll do it this way. Okay, so if we reach a leaf, then we create a tree with a bunch of branches. Otherwise, we do this recursively and create a tree with these new branches.
It looks better.
That works, at least for their one example. Let me describe how we got here. And then, they only gave us one example, so it might be wrong, but it seemed like it basically worked. It felt like in order to build this monstrosity from this original part, we needed to go through and call this apple function on 10 and 20 and 30 and anything else that was in the original t. So you get this like typical pattern for that. Like, how do you call a function on every label within a tree? You call it on the current label, and you call it on everything in each of the branches. And fortunately, we have a function that does that like recursively calls apple on everything in each branch. So this structure gives us a sense that we're going to be calling the apple function on every label in the original t. And what's unusual about this function is how you put together the results, because instead of like just getting a number back, you get a whole tree back. There's no like good way to place all these trees. So whoever invented this question decided that we were going to duplicate parts of it all over the place and then graph them in. And that's how we came up with this. Okay, so this basically says, go until you hit a leaf and then put all the branches on that leaf. And otherwise, go search the tree until you find leaves. So this is a fine way to do it. Yeah, good question. So the question is, how do you, like, since the output tree is a different structure than the input tree, how is it that we have kept track of the original tree well enough to build the output tree without kind of getting the two confused with each other and without changing the original tree? So one thing about changing is that we are just building new stuff all the time. We're not editing the contents of the original tree. We know that because we don't see any append, extend, element assignment, slice assignment, anything like that. All we're doing is going through the original tree and building new trees along the way. Now, how is it that we're building these new trees and still kind of keeping track of where we were in the original tree? And that's a great question. We're kind of relying on recursion to do that for us. So when we make a recursive call to village, we're making it on branches of the original tree. So all those calls to village that will happen along the way, because of the recursion, are going to be processing parts of the original tree. And there's no risk that they will instead be processing something else, because we only call village on parts of the original tree, which then calls village on parts of that original branch, etc. And the building of the new tree with the new structure only really happens in the return value to village, which does have this like unusual structure with a lot of repetition in it, but that all gets constructed after you've kind of gone through and made sure you call village on each node. Okay, so great question. The question is, what's the difference between adding to a list using plus versus using append? When you use plus, you create a new list. So if I have A and I have B and I write A plus B, A hasn't changed and B hasn't changed. And in fact, I could write something like C equals A plus B. And now C, A is that, B is that, and C is that. So we have 3 different lists, whereas originally we had 2.
And to be clear, if we change A now, C doesn't change, right? It is really a new list.
Oh, that is right. If I, get rid of the contents of A, now A is empty, but B is still there and C is still there. Okay, so that's how plus works, is it always just creates a new list. What about append? If I have 2 names for the same list and I append to A has changed. We see that change reflected in B, because A is B. These are just two different names for the same list. So append changes this list. But the other quirky thing about append is that it doesn't return anything. So if I said something like C equals A dot append 4, what's A? It's now got 1, 2, 3, 4 in it. B does too. And what's C? Well, C is actually none. The return value of a call to append is none. Why does that make sense? Well, append does something to A, but it doesn't really create anything new, which is why it doesn't have a return value, or the return value is none. So instead of adding where we made a new list, we're just changing an old list. I guess the last thing I'll say on this issue is that if we wanted to put these things together, you might imagine something like A and B and C, where A is C. Or if I said something like A equals A plus B, now I'm making a new list and assigning it to A. So A is 1, 2, 3, 4, and B is 3, 4, and C is still a name for that original list, 1, 2, which used to be called A, but now A has been used for something else. Okay, I'm going to go for another 1 minute and say my least favorite thing about Python. And that's a lot because there's a lot of problems with Python. But one of them is that it has a plus equals operator that kind of does not what I'd expect. So watch this. If I set A to 1, 2, and B equal to 3, 4, and C equal to A, everything's the same because I haven't done anything different. If I replace this line with A plus equals B instead of A equals B, now A is 1, 2, 3, 4, B is 3, 4, and C is different. Meaning this doesn't actually mean the same thing as this. I made some effort to get these to line up nicely, but somehow I failed. Maybe the font size is different or something. But you should just be aware that if you have a list on the left side of a plus equals, then something weird happens. That's a lot like extend. And so I almost never use this construction because I don't trust it. I feel like it should do the same thing as that, but it doesn't. So now that you've learned about, this has been like a theme of this Q&A session, is that Python has all these weird quirks. And, you know, that's true. Other languages also have weird quirks. You may not have learned about all of them, so you might think things are rosier on the other side. Usually they're not. There is a notable exception, a language that basically has very few quirks, and that is called Lisp. And we will learn about that later in this semester. And it is quite internally consistent.